Good afternoon, everybody. Welcome back from the break. Okay, now, in a solar atmosphere, that we want to look at MHD waves. We try to see the propagation. We look at the propagation of these waves. We look at propagation of MHD waves. There are regions to which we can work on. It's either we look at corona, we look at photosphere, and then we look at chromosphere. These are typical areas of our contributions. And these things, these layers, actually depend on the plasma beta. Depend on plasma beta. If the plasma beta is equal to 1, we look at that as degenerate state of the equilibrium. So whenever the beta is equal to 1, we consider it as degenerate states. And then if beta is far less than 1, we look at the corona. And then when beta is greater than 1, we look at the photosphere. And then each of these layers actually have their parameters. There are parameters that are associated with them with the magnetic field strength. Because the beta is defined as the gas pressure over the magnetic pressure. So everything there will depend on the strength of the magnetic field and then the pressure. So if we want to look at a work or research topics, normally for their class we begin to look at equilibrium states. We can now begin to look at equilibrium states. So I just want to talk about it. By tomorrow, I'll come out with concrete topics we can work on. So we can look at these topics, equilibrium. When we look at the equilibrium states, we have done that with constant magnetic field. We say magnetic field is what? Constant at B0 at equilibrium. B0 is constant, P0 is constant, rho 0 is also constant. And then this one will vanish, V0. So we can see that we discuss equilibrium within these limits. And of course, we ignored the magnetic tension. In case magnetic tension is there, what are we going to do? We solve this problem with gravity and without gravity. And we can now see the effect of gravity on the equilibrium state of this plasma at various levels. Good. Now, we can go to number 2 to look at the propagation of waves. Which we have done when G is different from 0 and when G is equal to 0. Is it not? Huh? That's what we have done. Now, we also did this when the magnetic field is 0. And we also did it when the magnetic field is different from 0. These are things we have considered in the last couple of our lectures. Now, there are things that will come when we try to consider what we can look at inhomogeneous magnetic field, when the magnetic field is not constant. So we can look at that. We still have to look at inhomogeneity in magnetic fields. In this case, it's not a constant. What may happen to linear waves generation? So we can look at linear wave generation, or you look at it as propagation. That is one thing we can look at. See how this, and then try to work within the region of free force, force-free environment, as we did, and then see the effect of G, and then see the effect of what? Gravity. So here we can now see the effect of gravity. And when we come to the effect of gravity, gravity introduces some other things because the environment now is stratified. We can now go on to look at cutoff periods in this. So we might look at issue of cutoff frequency. So when we look at cutoff frequency, we now begin to see how we will. We consider isotomal, where there is no change in temperature over a very long time. We can also look at non-isotomal. You see how we're going to go? Non-isotomal and non-isotomal environments. So we look at isotomal and then non-isotomal environments. So there are quite a lot of things we can come out with. But the thing is, everything depends on our ability to handle the mathematics. If maths is good, you discover that these things are not really too difficult. And we can also begin to look at heat function, because there's no way we can walk in the atmosphere, solar atmosphere, that there won't be heat function. So we can look at things that come with thermal imbalance. That will be the third area. What is happening to these our markers today now? Thermal imbalance. And then we begin to look at heat function. So that if you go on and on, you may begin to look at things later as you grow. You know, they said when you take a bird, a chicken, to a new place, what it does is to walk with one leg. Then when it stabilizes, it begins to walk and can fight in that community and begin to have its own colony. If it's a rooster, is it not? So I want you to have your own colony where you can get others involved. And then maybe by the time you get through these processes, the next thing is instability, which we did not discuss in this class. We look at Kelvin, Helmholtz equilibrium, Rayleigh-Taylor's, and all the other processes. So I will go this evening, as we said. I've listed these areas. I'll be able to get concrete areas, topics, which can advance some research. Like as I was seated there, something came to me. I was trying to prefer a solution to one of the wave equations. That was what kept me. You went playing with your phone. And I forgot that I've not called my son since morning. You know, it's just now that I went out. And he's telling me that I've forgotten him. I said, no. Okay. Like the paper I was working on, I will give you this to try this evening. And let me see how ready you could be to work with. I know you want to work with me. No, this one, everybody is quiet. You see, my cross is not too heavy to carry. The only thing that my cross needs is that you don't forget what you have learned all through your life. And that one makes your brain okay. I remember those days at Grandson Laboratory, the underground laboratory we have in ICTP. We could stay there, work for hours. The only thing you can take is either you take ice cubes, put water, or you take Coke and put in that place. It sustains you for hours. How many of you, small time now, you want to go and eat? There is tuwo. Now, let's see if we can try this. We have come across this. I want to see you work on it. Please, it's very important. That will determine what we will do. All of us should try. Now, you see this equation. We came across this equation, is it not? We came across this equation. This is the contribution of G. If I remove this, everything follows, is it not? Okay. Now, what I want us to do, one, you remember that your CS squared is equal to gamma P naught over rho naught. Who can remember how we did the height scale? What is our H? Can anybody remember? And can anybody also remember that we wrote temperature? T0 is equal to T0 is equal to P0 all over R rho 0. That is gas, ID gas law. Okay. Now, can't we remember this one? Have you forgotten? Name and Taco? Okay. I wrote it somewhere. We said that, what am I even saying? H. How did I define H for you? H is actually given by H is given by CS squared. I'm making this blunt. CS squared over gamma G is our check. Is it not? So I want you to look at this equation with all these parameters we are given. We need a solution for V, Z, and T. So we can take this solution to be of the form F of Z multiplied by EI omega T. So we'll make this substitution. All right? We'll make this substitution in this equation. So I just want you to go home, put this in this equation, and then make use of this. And the next thing I will do is for you to take T. T0, take T0 as a function of Z, which means you are now going to use this formula. You are going to use this because there's nowhere T is here, but T is introduced by this and by this. You remember? Rho 0, P0 over rho 0, P0 over rho 0 is given as what? T0 over R, is it not? So I can now put T0 over R in this equation, and the CS squared will not take that value. So I want you to assume that T0 is equal to beta Z. We call this that B is linearly related to that. And that tells you that the temperature, the linear temperature, instead of being constant, it has a linear, it varies with Z, but linearly, that the graph looks like this. This is when beta is 0. Okay? It varies like this. This is T0. Have you heard about what we call Bosniak approximation? That relates the pressure, the density with temperature. Particularly if you are working in optically thin or optically gray environments. So you see, and all of them depends on the Boltzmann's constant. Okay, so we look at this. I want you, now listen, I want the solution tomorrow. Collect extra sheets of paper. Huh? Okay. You are given this equation. We want a solution of it in this form. And then you are given all this. Which means in this thing you are going to do for me, there won't be CS squared. Because it's the CS squared that linked the temperature that will give you this. Let's see whether we'll be able to achieve to have an equation that looks like bezels. Then we quote the answer. Huh? Okay. So that's the areas which we are going to look at on cutoff frequencies, the equilibrium, the magnetoacoustic waves. These are the three areas we can generate some problems. Either uniform magnetic field or inhomogeneous magnetic field, so that we can be working even as I go You have my contact, you have my email. We can be exchanging work. And at the end of the day, we have a collaboration. Thank you. Sir? You see here? If you take it and put here, now when you put it there, look at this. It has a P0 over rho 0, which will link it with temperature. So temperature enters there. And then once the temperature enters there, you make this substitution. You get some equations. The answer might be something that has to do with gamma function. It will also relate it to bezels. So but we'll just see it and see how the solution will look like. You might get somewhere that you might not have the answer. So what you do, you resort to what? Numerical. Oh no, you're welcome, sir.
Now, let me say this. Whether you like it or not, we're going to work in both sides. And the reason is very simple. How many of you here have up to 15 papers? Or how many of you are lecturers? How many of you have up to 15 papers in Elsevier journals? What area? Any area.
Put your papers together.
What I'm saying is, you see, one of the things we have to do is, it will broaden your research capacity. Right? I know we've not done it for, but the prof has done a lot of the foundation here. So I want us to open our minds to take a lot from this and take a lot from you. We're going to have a critical
This time. As a young researcher, your mind needs to be open. If you have been very keen from the beginning, even from when Prof started, he told you he started with mathematics, he went to high energy, he is in fluid, he is in that. So as a young researcher, don't limit your mind to something, because you don't know where your opening can come from. If you have the opportunity to learn anything, learn it and learn it well. And learn it well. It will help you. It will help you. So don't just think you are just here. You are here to learn something. That thing might change your future tomorrow. Okay? So as a researcher, please don't limit your mind. Even as he's lecturing, I'm still struggling to jot, because I'm still seeing that I can push something in that area. Okay, so please, I just want to encourage you to open up your minds and make the best of this opportunity. Make the best of this opportunity. Okay. So I will just throw more light on the first research objective. Then we can go. Okay. So what would that objective be? To derive Einstein's gravitational field equations exterior to plasma spherical stars. That's our first objective, which some of you will work on. Okay? And the first thing you are going to do is to review related works on gravitational fields exterior to spherical stars. Okay? So that's the first thing. All my students, your first paper you publish is a review paper. At MSc, at PhD. The first paper you publish is a review paper. Okay? So I expect us within a day or two to go through at least 50. Okay, at least 50 works, 50 related works on this. And then try to appreciate what others are doing. Okay? Try to appreciate what others are doing. Then after that, then we will now use Borisova and Rabonsky's metric. Okay, exterior to plasma stars to derive our own field equations. So the metric, the Rabonsky and Borisova metric tensor is there. It's already there. There's one of my work I published with one of my students. He also used it. So you will get it. Once you have that metric tensor, then from there we start and go through the process I gave you some few days back. Okay? So the first task will be to get those field equations. And getting those field equations is good work. Okay? And then with our review, we can now be able to appreciate what we have gotten with what is existing. Do you get the point? We will now be able to appreciate that. So, with our field equations, we can be able to even publish. And then, thirdly, we'll now try to see if we can get at least a solution to one of the field equations. Okay? So if we are able to get to 2 successfully within a week, then we can get to 3. So basically, that is what we are going to do. So as a take home, I want you to come along with this metric tomorrow. I'm not going to give you this metric. So I want you to come along with Borisova and Rabonsky's metric tomorrow. So you come along with it tomorrow. Then from there, we'll now see how to start developing it. Okay? So this is our first objective that some of us are going to work on. The others, as we go along, we'll see others. I think there are about 5 or 6. They can even be 10. Okay? So basically, this is the first step. Okay? This is the first step. So is there any question? Now, guy, you want to say something? Yes. Yeah. Okay, if I can get some of the works. So what was the essence of giving you data? You go online and check. Those you cannot access, get back to me. I will get them for you. Okay. So the ones you cannot get, the ones that don't have free access, get back to me. I will give them to you. That is it. That is it. It's part of your research training. Okay? It's part of the research training. You should be able to look for related works, source for related works.
That is it.
In less than 3 hours, you're able
Okay. I hope you are okay. Any other question? Any other question? Okay, so please let's be ready to walk. Let's be ready to walk.
I'm already seeing them now.
Okay, you're already seeing them.
Mistakes and progress of
Yes.
and it's a review of progress of it's very strong development.
Okay, so we'll continue from there tomorrow. Tomorrow we'll finish the others, and then we'll now try to see how we group ourselves, and then from there we can move on. Okay. No, we can we this is just one for one group. Okay. Anyway, let the okay, all work together. Anyway, we agree on that. Prof, you think them working together is better? The group will be too large. Okay.
Since we also be part of
Yes.